Okay, I think this makes sense also to do as a Venn diagram. I guess there's probably other ways to do it, but well, you know what? Let's try not with a Venn diagram first, and then let's do it with, and then you can see why it's okay to do it the way we did. Okay, so because you remember the equations here, if we're trying to find A and B, where is it? A and B is A times B given A. Can I do that here? Oh, A and B. So the probability of A and B, let's just say it this way. Probability of A and B is, you can always do it this way. It's a probability of, let's look at that again, because it's kind of backwards here from before. What I have is A given B. So A given B, I've got these backwards here. So I should do B times A given B. This is the probability of B times A given B. Not sure if you can remember that. The equation will be on the formula sheet, but let's see what we get here. So the probability of A given B, this is, probability of B is there, it's 0.4. Probability of A given B, that's there, it's 0.3. So that should be 0.12. Let's do this by Venn diagram, and let's see if we would get the same thing. All right, so we have A and B. We don't know if they're independent or not. That question's coming in part B. So say you forget this formula. I'm just going to see there's another way to do this. We know that A total is supposed to be 70%, and B total is supposed to be 40%. But I know that A given B is 0.3. So I know that amongst B, so the probability, so that, I mean, another way to read that is, if you found the probability of both, the probability of A and B out of the probability of B. So in other words, the football is supposed to be 30% of the B. Okay, what does that mean? Well, this is supposed to be 30% of 0.4. What is 30% of, remember of means times, of 0.4? Well, that's supposed to be 0.12. That tells me this is 0.12. I don't know if that is really better than memorizing or looking up this equation, but because it's the exact same arithmetic, but that's what that means. This would then tell me that this is, if I wanted to fill out the rest of this, this is 28%, this is 58% to make these add up. And I can figure out what the total is too. The total is 70 plus 40 is 110, so I think the total is 98%. I think there's only 2% out here. 70 plus 20, yeah, it's 98. There's only 2% on the outside. Are the events A and B independent? Okay, so here's where you need to show a calculation to show, are these independent or not? If they're independent, this is my favorite one. If they're independent, where is it? There it is. If they're independent, then this ought to work. That you should be able to multiply the probability of A times the probability of B, and it should equal the probability of both. And we know all these probabilities. We just have to check and see if that works. So if this is supposed to be independent, we just have to check probability of A times the probability of B is supposed to equal the probability of both. Is that true? Well, probability of A is 0.7. Probability of B is 0.4. Probability of both is 0.12. This is not true. This is 0.28. This is 0.2. So no, we'll say not independent. We knew that way back here, actually. The probability, I mean, even from looking at this, you can look at this. The probability of A given B is 30%. The probability of A in the first place is 70%. So overall, generally speaking, amongst the population, we have 70% A's. You go to the B party, you only find 30% A's. That's not the same. So by being in the B crowd, we know we've reduced our chance of finding an A person. So these are definitely not independent. They sort of repel each other. There's less A's among B's than there are A's in the population. So that's not independent. All right, you don't have to say it that way when you do it. When you say it, you can just say it this way. Say that you pick your favorite equation, either that one, or you can also use this one. If the probability of B given A equals B, and actually that's already there. That was the one that was already at the top. Yeah, let's do that one. If they're independent, okay, so the one way to check is that multiplication one. The other one we could check is, does the probability of A given B actually equal the probability of A before you even put the given B on there? Just check that. Well, that's even easier because this was 0.3 and this was 0.7. Those are given, and that's not equal. So we're done right there. Okay. Can contains 4 blue and 2 green. One marble is randomly drawn without replacement from the can, and its color is noted. A second marble is then drawn, draw a tree diagram, and determine the probability of, well, let's do the probabilities first. So I'm not going to do the thing. We just did this earlier in 13.5. I don't think it was yesterday, but it was in our recent past. All right, we have some blue and some green, and we have 4 blue and 2 green. So we had a 4 out of 6 chance that the first one is blue. We have a 2 out of 6 chance that the first one's green. After the first one's blue, we have 5 left in the can. How many of those are blue and how many of those are green? If we pick a blue first, we're down to 3 blues, but we still have, oh wait, that wasn't blue, that was green. Oops. Oh, I can't move that separately? You're kidding me. Sorry, that was supposed to be green. We have 3 blues and 2 greens left. I'm gonna want that green dot there. If we pick a green first, we're gonna have in the 5 marble can, there's only gonna be 1 green, but there's still gonna be 4 blues. All right, does this make sense now? I should have done all this before I start talking to you guys. Okay, so draw a tree diagram. Let's talk about all these possibilities. This possibility is, if I multiply, this is 12 out of 30. This is 8 out of 30. This is 8 out of 30, and this is 2 out of 30. Hopefully that adds up to 30 out of 30. Yeah, it does. And remember, those possibilities look like this. This is both being blue. This is a blue followed by a green. This is a green followed by a blue. And the other one is 2 greens. I'll put these in here so we know what those look like. So this is essentially the sample space and their probabilities right there. That's the part I care about. Okay, I'm going to want that on the next page. So now we're ready to talk about this. What's the probability that the second marble is blue? Well, that would be in this category or this category. So that's the 12 out of 30, or, remember, or means plus, the 8 out of 30. In other words, 20 out of 30, which is 2/3 of the time. First was green. Given that, second one was blue. So, second one was blue. Probability that the second one was blue. Oh, good. I have that done already. So out of those 2/3 of the time, I need to know the probability that the first one was green and the second one was blue. Remember, this is of these 2/3. So out of these and these, how many of those have the first one being green? That's only this many. This is the probability of both those things happening. Remember, this is the intersection over just the one that's given. This is 8/30ths out of 2/3. As a fraction, you can compute that this way. That's 8/30ths times 3/2. Remember, invert and multiply for dividing by fractions. This is not a fun fraction to have to do. This is 24 out of 60. That's probably a faster way to do that. Divide top and bottom by 6. And I can go one more. This is 2/5 of the time. Okay, that's it. Thought this would be short. Okay, I will see you at school.